All right, so in that last video, we actually went through a nice little algorithm that decided this language of this block of zeros followed by a block of ones of the same length in about big O of n squared time. So this kind of first approach that everybody has when they begin playing with this language. The idea here was to kind of dance around this little tape. You find a zero, you find a one, you find a zero, you find a one. You go back and forth, and I've already committed, so I might as well keep on drawing. All right, so you can see for this nice little string that had 14 overall symbols, I had to essentially move my hand back and forth about 7 times. And then I had to read across the entire thing that many times as well. So you end up getting something that looks essentially like an n squared over 2 times an n, which basically became this big O of n squared. So our quest now is to try to improve that a little bit. I want to do better. Big O of n squared is fine and dandy, but I want to really think about, can I maybe squeeze a little bit more out of it? Maybe there's a step in that process that I could do a little bit more efficiently. At this point in time, it is worth mentioning essentially kind of what is the kind of best thing that we could actually even be shooting for. That is, how much effort does it take to even just read something on one of these tapes? So if I were to start here and go all the way across, well, there's 14 symbols there. I'm going to have to move my head 14 times. So absolutely best case scenario would be something like big O of n. That's like the truly aspirational thing that we could not do any better than that. What you can see over on this left-hand side is a little bit of a spoiler alert in that we're not going to get all the way to big O of n, not yet. And the next example, when I straight up cheat, we'll get there. But for right now, on a single tape, the best we can do is going to be running in about n log n, which is a pretty big improvement from the n squared we were before. So the way that we're going to do this is a pretty clever approach in that as we pass through this thing, we're not going to simply remove 1 0 and 1 1. We're going to remove more than that each step. That does come with its own little complication in that we really need to begin kind of making sure that the number of zeros aligns with the number of ones. So the way that we're going to do this is actually jumping back to that little point that I made in the first video that said, okay, hear this thing and then put it in the back of your brain, store it for a rainy day. Now is that rainy day. So if you have this initial input that has 14 symbols, that at least has the potential to be a perfect split of zeros and ones. Here you can see that it would be exactly 14 divided by 2, or 7 zeros and 7 ones. If the initial string had something like 15 symbols, you know that it's completely garbage. There's no way that that's going to be accepted. That's actually going to come into play as we begin parsing through this string. What's going to happen is that each time I pass through, I'm going to make sure that I have an even number of interesting symbols on my tape. I don't care about the blanks and the X's that I'm going to form. Just the remaining zeros and ones are going to have to be even still. If I ever flip into something that's odd, I know that I'm going to actually reject this thing. So once we run through an example, I'll show you kind of what can happen if we have a mismatch and where that's actually going to emerge from. So the way that we're going to do this thing is I'm going to, again, kind of look at that thing and make sure that it's big picture, a bunch of zeros followed by a bunch of ones. That you can do in big O of n. So really fast. So do that once, go back to the beginning and say, okay, now I know that it looks like some zeros followed by some ones. So as I begin to cross off things, I can cross them off kind of all willy-nilly, and I don't really care about having to run into a 1 before a 0. So the way that we're going to do this is I'm going to see that very first 0. I'm not going to immediately go on a quest looking for ones. I'm going to go on a quest looking for more zeros. Namely, I'm going to go on a quest looking for every other 0. And I'm going to cross all of those off. And you can see right from the beginning that that's a pretty tremendous savings. I went from having 7 zeros down to 3 zeros in one overall pass. Previously, that took me like 4 steps because I had to cross off one, and then another one, and then another one, and then another one. So you can see right from the get-go that this is going to speed up pretty dramatically. I do the exact same thing for the ones. So I'm going to have 7 ones. Now I'm down to 3 ones. The thing to note at this point in time is how many non-X and non-blank symbols do I have? Well, I have 3 zeros and 3 ones, so that tells me I have 6 overall things that I have to play with, which is still an even number. So next I'm going to cross off half of those zeros, in that I'm going to start with the first 0 and then I'm going to do every other one. So half is kind of in quotes, and that's going to be an important concept in a little bit, but I'm essentially cutting off half the number every single time. Same thing with the ones. Cross off the first one, cross off every other one, leaving me with 2 symbols left on my tape, and those both die off in the next pass, and hooray, everything is X'd out, so I know that that thing is honestly going to be accepted. So what can go wrong? So as I mentioned, I want to keep track of this evenness as we go. So if you were to have, let's say, something that had 1, 2, 3, 4, 5 zeros and maybe only 1, 2, 3 ones. So initially that thing has what, 8 overall symbols? So you're like, okay, that has the potential to work. It could be 4 zeros followed by 4 ones. It's got the right shape. It's zeros followed by ones. So initially everything seems great up until you start crossing things off. So if you cross off every other 0 and every other 1, you can see that very quickly you're down to 3 symbols. And at that point in time, there's no chance that this can be perfectly split anymore. You can't take 3 things and perfectly divide it in half. You can see that you have a mismatch of the number of zeros to the number of ones. And that's exactly why that thing would then be rejected. Because otherwise you could keep on dancing around and you might end up crossing off too much stuff, or you might see some kind of weird, funky things happen. So that's going to be the check that we go, is that each time we're going to make sure that we have an even number of things and then do this dance of removing everything afterwards. So how many steps or iterations did that actually take? So again, I had 14 overall symbols on my tape. It only took essentially 3 big passes to construct this nice little rectangle. We officially had the initial pass that made sure it was the 0 ones, but that happens in linear time, so I don't really care about that. And we have that last pass to make sure that it was all X's. Again, that's linear. I don't really care about that. The bulk of it's going to be in that middle bit, that kind of typewriter writing back and forth, back and forth. So what ends up happening there is that I have about 3 rows. And then each of those rows I'm going to read all the way from left to right. That 3 is very special in that it plays really nicely with the number 14 that we started with. It plays nicely once I start looking in powers of 2. So the powers of 2 are hopefully kind of obvious as we go through this process. We were removing about half. It gets a little bit more obvious of the half when you begin looking at powers of 2. 14 is not a power of 2, so sometimes we removed more than half, sometimes we removed less than half. Obviously that first pass we went from 7 down to 3. So we actually removed a whole bunch. And then we went down from 3 to 1. We again removed more than half. And then the very last one, we actually removed everything. So we're removing about a half. So what that means for us is we can actually record the number of steps by seeing the largest power of 2 that's inside of 14. Essentially, we're rounding 14 down to the nearest power of 2. The way that we can do that formally is you write 14 as some power of 2 plus some stuff, and then you look for what that little special exponent is, so that nice little 3. The way that we can get that 3 then is we're going to use a logarithm. So logarithms are brilliantly designed to give us these exponents. So if I were to take log base 2, so again 2 is the cutting everything in half, and then I'm evaluating that thing at 14, that's going to give me exactly the exponent that 2 raised to that thing makes 14. So it's going to be some number between 3 and 4, a little bit closer to 4. What I want to do is I want to round that thing down. I want to take the floor of that object. So that thing tells me exactly the number of rows that I'm going to have in play. At this point in time, it's worth looking at one of these that is honestly a power of 2, so then everything becomes very obvious as where everything comes from. So if I looked at n being 16, so again, initially, right from the get-go, it seems like at least seems plausible because 16 is even, so I could have 8 zeros and 8 ones. So on first pass, I killed off exactly half the zeros. I went from, 8 down to 4. Same thing with the ones. I went from 8 down to 4, so I have 8 overall symbols left on my tape. Again, an even number. Now I'm going to take those 4 zeros and chunk them down into 2 zeros. And then those 2 are going to go down into 1, and then the 1 is going to go away. So you get this perfect removal of half of them every single step. Again, you get a perfect even number as you go as well. And then at the end, you get all of these nice little X's emerging, which is to say that that thing is honestly going to be accepted. So here you can see how many iterations do we have? Well, it's going to come from the n being 16. 16 is nicely 2 to the 4th, and that 4 is exactly the number of moves that we need. So what ends up happening is that if you were to look at big kind of complexity of all this, you again are going to have this kind of funky little rectangle. What you want to think about is the width of this rectangle is an n, and then the height of this rectangle is not going to be another n, it's going to be this fancy little exponent. So here it was a 4, and that 4 is log base 2 of n. So when you multiply those two things together, you're going to get log base 2 of n multiplied by an n. And that actually tells me the complexity of this process. So it's better than n squared. It's quite a bit better than n squared. It's again not as good as big O of n, because we have this extra little smudge factor. There is some width to this rectangle, but it's not nearly as big as the previous one was. So there's not a ton of rows. Logs are really nice. They grow super duper slow. So even if n was, 2 to the 10,000th, what's going to happen is that you're going to have a really wide thing, but it's not going to be very tall. I mean, it's still going to be pretty tall, but it's going to be much less tall than if I had 2 to the 10,000 divided by 2 number of rows. So it's a tremendous amount of savings in that we can burn through this process pretty quickly. So you can write this as this log base 2 of n. There actually is other ways you can represent this as well. And that actually comes from a little bit of college algebra, in that if you were to look at log base 2 of n, via a change of base formula, you could write this as just a log of n divided by a log of 2. So what ends up happening is that this is just some random constant, and this big O world doesn't care about constants at all, so you could drop the 2, and I guess a whole bunch of other symbols. So you could drop the 2 and just say that this thing runs in n log n, and you could choose whatever base you wanted to. I happened to use base 2 originally, but you could actually choose a different base. Big picture, it's going to be n log n. If you wanted to see this thing run for n being 18, same exact process is going to happen. You're going to chunk a whole bunch of those zeros down. The 18, again, is going to be really close to a 16. It's actually 2 larger than it. So the number of rows that are going to occur here are going to be, again, you take this log base 2 of 18 and you floor it, which gives you a 4. So here's where I have this nice little indication of how long this process actually took, as well as the nice little college algebra fact about how this change of base is actually going to work. So we get a really big savings. We went from n squared all the way down to n log n. We're still not at the kind of theoretical best case big O of n. We'll get there in a little bit, but it does in fact require a little bit of cheating. So as long as we're okay with cheating a little bit, then we'll get all the way down to n. But without cheating, this is actually the best that we can do. We can do no better for this particular argument. It's pretty nice, it's pretty tidy, it doesn't take a ton of steps, and we actually can't do any better. So we can confidently say that this is the least complex machine, and that it takes the least amount of effort to actually go through it.